Step on up, step on up. Solve this chemistry equation and win one stuffed jaguar. Any takers, any takers? Chemistry? Like the periodic table? Easy, I'm coming over. Yes, I see you, sir. Come on over. Attempt this problem or might be your lucky day. Listen, old man. I don't even want this stupid jaguar. I just want to prove to you that I can do a simple chemistry equation. Like, why are you even at the circus asking people these equations in the first place? Oh, so you think you know a little bit about chemistry, do ya? Well, sir, I hope you get it right then. Just show it to me. I can take it. The problem in question is this. Vector addition. Now, tell me, sir, what is the total dipole moment on this hydrogen molecule, Wait a minute. Vector addition? What? What? You mean to tell me you don't know about vector addition and total dipole moments? Oh! Silly man! It is so simple. Look here. Oh.
We can start off with what is a vector. Well, by definition, a vector is a quantity that is fully described by having a magnitude and a direction. Magnitude is usually a form of measurement, so you can think centimeters, meters. Then directions can be north, east, south, west, etc. Essentially, you can think of a vector as an arrow. Vector addition. Vectors can be summed by adding their magnitudes and directions. This is akin to placing vectors end to end and seeing the net direction traveled. So here we have the v vector here and the w vector here, and they result in the red vector that shows the net direction traveled. This was done by taking the v vector and placing the w vector at the very end of its tip. Atoms and molecules. Atoms are natural single forms of elements on the periodic table. When two or more atoms bond to each other, they are referred to as a molecule. Typically, atoms bond to each other and form molecules through covalent bonding. This is when atoms share the electrons in their outermost electron shell, which are called their valence electrons, to fully fill in those shells and become stable. In the diagram to the right, we have oxygen, which has 6 valence electrons and it wants a total of 8. Hydrogen has 1 valence electron each. So if the oxygen bonds to the 2 hydrogens, all 3 will be happy and have full valence electron shells, and this is essentially water. Now, the definition of electronegativity is the ability of atoms to attract electrons. Some atoms are more electronegative than others, meaning they will take another's bonding electrons more readily. Electronegativity increases as one goes up and to the right of the periodic table. So as you go up and to the right, electronegativity increases, which means that nitrogen, oxygen, and fluorine are going to be our most electronegative atoms on the table. Charge separation. Because some atoms are more electronegative than others, like nitrogen, oxygen, fluorine, this difference can cause electrons in a covalent bond to be unevenly distributed or shared. This uneven distribution of electrons results in one atom having a partial negative charge and the other having a partial positive charge. Molecules with charge separation are called polar molecules. Now, here we have carbon bonded to hydrogen. Because the difference in electronegativity is small, there's going to be no polarity here, so the molecule is nonpolar. Here we have carbon bonded to oxygen, and because oxygen is more electronegative, it's going to pull the electrons from the carbon towards it. Now, this arrow is called a dipole. A dipole is a vector that comes from a covalent bond that has a positive end and a negative end. The dipole always points towards the negative end, which indicates where the electrons are flowing. So in this instance, because the electrons are flowing from the carbon to the oxygen has more electrons and has a partial negative charge. Meanwhile, the carbon is losing electrons, so it's going to have a partial positive charge. Now, molecular geometry. The degree or the polarity of charge separation of a polar molecule depends on the shape of the molecule itself. If a triatomic molecule has an angle of separation of 180 degrees, the molecule has a linear electron pair geometry. Take this for example. It's a straight line, it's essentially linear. Now, this linear geometry would result in two bond dipoles that start at the carbon and end at the two oxygens. And we can see that here, because oxygen is more electronegative than carbon, so it will pull on the carbon's electrons. Now, even though the molecule is polar, there is no total dipole moment on it because the two vectors are equal, thus they cancel out. This vector, or dipole, is equal to this vector, or dipole, so they cancel out and there is no total dipole moment on it. Meaning, the electrons basically are tugged on both sides equally and remain in place on the carbon. Now, water is a triatomic molecule. The central atom, oxygen, is bonded to two hydrogen atoms. However, its molecular geometry is not linear. This is because oxygen has two non-bonding pairs of electrons in its valence shell. These two non-bonding pairs of electrons serve as electron clouds that repel the covalent bonds with the hydrogens, giving the water a bent geometry. So here we have a bonding pair here and a non-bonding pair here, and these clouds repel the covalent bonds of the hydrogen and give the molecule a bent geometry rather than a linear one. Now, what is the total dipole moment on this water molecule, huh? Let's see. So we have oxygen and it has 6 valence electrons and it's missing 2. Thankfully it sees 2 lovely hydrogens and it immediately falls in love. Why? Well, that's because the hydrogens have 1 valence electron each and are missing 1. The oxygen slides in, they all fall in love and form covalent bonds. Now, because oxygen is more electronegative, it's going to pull those electrons closer, giving it a partial negative charge, while the hydrogens have lost their electrons and have a partial positive charge. Now, this flow of electrons results in dipoles that flow towards the oxygen. Now, because oxygen actually has a bent geometry, the dipole moment will look like this with an arrow going straight up. Now, why is this? Well, because to add vectors, you just simply stack them end to end, and you get the total dipole moment.
Now, don't you feel like an idiot, good sir? Now, let me tell you something. Idiots don't get jaguars. They get vector arrows. Ah! Wait, man. I'm sorry. I didn't know it was gonna be about vector addition and total dipole moments. Like, what even is that? Like, chill, please. Calm down. Oh, God. Whoa. Go long, sir. Make a run for it. Curse you, total dipole moments. Maybe next time, sir.
Now, the next time you're at the circus and a strange man asks you to solve a total dipole moment question, I hope you're able to solve it. Otherwise, you might end up like this guy.